In this video, I'm going to work through the Math 152 Usubstitution integration worksheet. Again, if you have the worksheet printed off, it might, or if you've already done it even, it might be a good idea to print off a new one and just work through it from scratch. And you can check yourself as you go so you don't wreck yourself. And so anyway, here we go. Here's the number one. Says x times cosine x squared. Remember, when you're doing Usubstitution, you're looking for an inside function, and you're also at the same time kind of looking for something on the outside that matches the derivative of the inside. So in this case, you can see that x squared is definitely inside a cosine, so that's a dead giveaway for that to be the u. So this makes me, just on first impression, think it seems like u squared. I'm sorry, u would be x squared would be a good choice for u. And then you notice right away when you make du, that would be 2x dx. You can see that this is very similar to that. So that little piece on the outside matches fairly closely to the du, because you got the 2x matches with that, you got the dx matches with the dx, of course. And so when we go to recreate the integral, which is the goal in Usubstitution, you want to come up with an integral that's just like this but involves u. So you'd say the integral of, and that's clearly going to be cosine u. Oops. Cosine u. And then, of course, we have to have a du because we're integrating something involving u. And so then you look to see if... Go. So we have the cosine u du. So notice that this is the same as that. The cosine u is the same as the original one, except for the du brings in an extra 2 that we don't want. So we counteract that by putting a 1/2 out front. So now, again, it's important to make sure that they match exactly. You don't want them to sort of match, you want to match exactly. So if I highlight the du and the 1/2, those together match up with the x and the dx. And if I highlight the cosine u in the green, notice that's exactly the same as the cosine x squared. So we have a 1-to-1 correspondence between these two integrals. So then I'm ready to go ahead and integrate it. Of course, that's a really nice and easy integral. The derivative of cosine comes from sine, and you have to ask yourself, is the derivative of sine equal to cosine? And yes, it doesn't need any negatives or positives because the derivative of sine is positive cosine, so that works. Of course, it doesn't produce an extra 1/2, so we have to bring the 1/2 along for the ride. And that would be my integral. Of course, I got to sub back in. So my final answer would be 1/2 sine of x squared plus c. Okay, moving right along to number 2. Once again, I think we talked about this one in class, but you notice that there isn't really a clear inside-outside here, but I do notice that x to the 4th is pretty close to the derivative of x to the 5th minus 17. So that gives me the idea to let u equal x to the 5th minus 17. And then we know du is 5x to the 4th. So then when we go to rebuild the integral, we're going to have a u on the bottom and a du on the top. And of course, here, the du brings in a 5 that we don't want. There's no 5 sitting out here. There is an x to the 4th sitting there, but there's no 5. So it brings in an extra 5. So we can counteract that by putting a 1/5 out front. So now, once again, if we did our fun little highlighting, the du and the 1/5 matches up with the x to the 4th dx. Because you can see that 5x to the 4th with a 1/5 out front matches that. Okay? Or even maybe to make it even clearer, what we're counting on is that whoops. we're counting on, what we're suggesting is 1/5 of du is equal to x to the 4th dx. And you can see du, of course, is 5x, so that'd be 1/5 of 5x to the 4th is equal, whoops, 1/5 of, I forgot my dx up there, 1/5 of 5x to the 4th dx is equal to x to the 4th dx, isn't it? Okay, so get rid of all that stuff, but now we're ready to integrate, and of course to integrate this, the integral of du over u is just ln u, and the 1/5 goes along for the ride, plus c, and so that's equal to 1/5 ln of x to the 5th minus 17 plus c. Actually, when you integrate, if the answer to your integral is natural log, you want to put absolute value around it, because remember, natural log cannot be, you can't take the natural log of a negative or 0. So, okay, number 3. This is, I did a separate video on these types where you have two trig functions to raise to a power and multiply together. So that would be another good video to watch, because there is a kind of whole family of Usubstitution problems that are like that. And the goal here is to pick, the du has to be sine or cosine, which means the u has to be sine or cosine depending on which one you want for du. And the way you decide is, now in this case, there's an odd number of factors of sine and an odd number of factors of cosine, so it doesn't really matter. You want an extra factor of one or the other. So in this case, I think I will choose my du to be cosine x dx. That means it only leave one cosine, or cosine squared, left over. So my integral would be sine of 5x cosine squared x cosine x dx. Again, in these types, you really kind of pick the du first, which means your u would have to be sine x, right? And so then if we bring out the fancy highlighting again, whoops, you can see that right there is my du, and that means all this other stuff needs to be turned into u's. So we can easily turn the sine into u's, but we can't turn the cosine into u's, so we're going to use the Pythagorean identity that says cosine squared is equal to 1 minus sine squared. So then I can rewrite this as the integral of sine of 5x times 1 minus sine squared x times cosine x dx. So you can see that we just replaced the cosine squared x here with the 1 minus sine squared x. And this is still that yellow here that we're going to replace with du. So now we're ready to actually make the substitution, which is very exciting. So I'm going to do the integral of u to the 5th times 1 minus u squared times du. So the integral of u to the 5th minus u to the 7th du. And this is a nice easy power rule, so this would be 1/6, and I'm going to change the u back to sine. I hope everyone's okay with that, to the 6th, and that's going to be 1/8 sine to the 8th power, and then plus c. Okay, on to number 4. This is a tricky one. We did this in class, but I'm just going to run through it again. Clearly, the inside function is x minus 1, but 2x is not the derivative of x minus 1, so I'm going to pick u to be x minus 1 and hope for the best. We notice that du is, of course, just dx, and that presents a problem because we still have this 2x out here that's not taken care of. This would be u to the 1/2. That would be du. And if we again try to make it clear with highlighting, it's amazing how wonderful highlighting is. This, whoops, sorry. This is supposed to be u to 1/2. So if I highlight this time instead of marking and highlighting, so that right there is the same as that right there. And to grab a different color, the du is the same as that, and we leave the 2x is left out. We can't have an x in there, we have to have something involving u. So I go back to my definition, and again, if I'm trying to define everything in terms of u, I'm going to solve for x here and find out that u plus 1 is equal to x. So that means I can replace the x with u plus 1. So then I have 2 times u plus 1. And so now I have an integral with everything, nothing but u's in it. And this, if I distribute the u to the 1/2 and the 2, I get 2u to the 3/2 plus 2u to the 1/2. And all that's times du. Okay? So then we can integrate. So when we integrate, we get u to the 5/2, and then I need a 4/5 to counteract the 5/2 and leave a 2 left over. And then we have a u to the 3/2, and then I need a 4/3 over here, plus c. Substitute the u back in, and we have 4/5 times, what was it, x minus 1? Yeah. X minus 1 to the 5/2 plus 4/3 x minus 1 to the 3/2 plus c. Okay, I'm going to kind of pick it up here because you're hopefully getting the hang of it. And of course, you could pause the video at any moment and rewatch it. This is another one that's a little bit confusing because there's not a clear inside function other than x, but making u x doesn't make sense because you're not changing anything. So in this case, we're looking, is there something that's the derivative of the other? So notice if I rewrite this as the integral, rewrite this as the integral of ln x times dx over x, that's the same thing, right? And you can see that dx over x is the derivative of ln x. So in that case, that makes me think, could I let u equal ln x? Then du is going to be dx over x. So when we change this to u's, notice it's just going to be u du, isn't it? Because again, if we bring out the highlighter, which I love to do, you can see clearly that that right there is the same as that, isn't it? You can see it over there, right? And of course, what's left, the u does, of course, match right up with ln x, as that's what we called it, right? And so the two integrals look the same. So we integrate this thing and we get 1/2 u squared plus c. And of course, that's just 1/2 ln x squared plus c. Make sure you put the whole ln x in parentheses because it's ln x squared, not ln of x squared. Make sure you make that distinction clear. All right, number 6, it looks like x squared is the derivative of 4x cubed plus 8, roughly, give or take a 4 or 2 or something like that. And 4x cubed plus 8 is definitely inside, so obvious choice for you to be 4x cubed plus 8 because it's on the inside and it has a somewhat of a derivative lurking outside. So du is going to be equal to, in this case, 12x squared, right? So it's not quite the outside stuff, but it's got an extra factor of 12. So when I build my u, I'm going to go sine of u du, and I notice the du brings in an extra 12 that I don't want, so I put a 1/12. Why did I put it outside the integral? Remember, you can put it inside or outside, it doesn't matter, because when you're multiplying by a number outside a function, if it's just a number and you're multiplying, it's just going to go along for the ride. So the integral is going to be 1/12, and the integral of sine is cosine. But notice if I take the derivative of cosine, I would get negative sine. Don't want that. I want positive sine, so I'm going to put a negative out front to counteract that. And I get a plus c here. And of course that would be equal to negative 1/12 cosine of 4x cubed plus 8 plus c. Clearly x cubed plus 1 is inside, and the outside looks remotely like the derivative, so I'm going to pick u to be x cubed plus 1. Therefore, du is equal to 3x squared. Oh my goodness, it's exactly the same. It's awesome. So then I take the integral of u to the 4th du, and the du, whoops, I forgot my dx here. Sorry about that. The 3x squared dx takes care of that and that. So it matches perfectly. So when we integrate that, we get 1/5 u to the 5th plus c, which of course is the same thing as 1/5 of x cubed plus 1 to the 5th plus c. Here's another one where there's a clear inside function, 1 plus sine x, and cosine is roughly the derivative. So I'm going to let u equal 1 plus sine x. Therefore, du is equal to cosine x dx. Perfect match. So then I run my integral of u to the 5/2 du, and it matches up perfectly. No extra factors or anything. So I just integrate, and I get u to the 7/2, which means I need a 2/7 out front, plus c. Resub it back in, we get 2/7 times 1 plus sine x to the 7/2 plus c. Okay, so 9, oh, this is another one of those ones. Like I said, I've made another video that kind of talks about the same thing. So you're looking for either you want your du to be either secant squared x dx or secant x tangent x dx. That's my two choices. If you take out, so if we want to rewrite this, let's see if the first one works. So we'll look at that. So that would be, so I'm taking out two secants, so that would be tangent cubed x times secant squared x times secant squared x dx. So my du is right there. Shoot, I keep doing that. Sorry about that. Secant squared x. So my du is right there. And that means if that is my du, that means I need to change everything to tangent, because that's the derivative of tangent. And I can change secant squared to tangent, so this will work. Now the other one might have worked also, but this one works, so it seems like it's pretty easy, so I'm going to go with it. So that means that I'm going to let u equal tangent. So then my integral is going to be tangent cubed x times 1 plus tangent squared, because that's what secant is, and that's secant squared x dx, right? So now I'm ready to make my substitutions. So that's going to be, it's going to be u cubed times 1 plus u squared times du. And I just checked, when I did this one in class, I did it the other way. I used secant x tangent x as a du, and so it does work the other way too. So if you want to see that, or I guess I didn't record that in class, but if you took notes on my class, you'll see it done the other way. So anyway, let's finish this. So this would be the integral of u to the 3rd plus u to the 5th du. And that, of course, is equal to 1/4. And u is tangent, remember, so I'm just going to sub that back in. Tangent to the 4th x plus 1/6 tangent to the 6th x plus c. Okay. So I think I'm going to pause the video here, or end the video here. Oh, no, I got one more. So let me do this one, then I'll do the definite integrals. I think, all 3 of the definite integrals in class. So let me finish this one. So u is equal to 4x cubed. Du is equal to x squared. What am I doing? Settle down here. 12x squared, right? So then my integral is going to be e to the u du. But of course there's an extra 12 here that's not there, so I need a 1/12. So when I integrate that, I get 1/12 e to the u plus c. And that would be 1/12 e to the 4x cubed plus c. All right. So I will finish this and post it.